Hello, this is the next video in a playlist that I'm calling Hypothesis Testing, and we're in the unbiased hypothesis testing phase. Previously, we have looked at two-sided simple versus composite, uniformly most powerful unbiased tests. Now we're in the two-sided composite versus composite hypothesis, uniformly most powerful unbiased test. And here we're going to conduct a test on the normal variance. Now you must see the video. The original theorem is in this video, unbiased hypothesis test, earlier in this playlist. And there we state the theorem that we're going to use for this test. Now after I go through several more examples, then we'll prove that theorem, but I wanted to go through the examples first. So here we're going to assume our data is normal with a mean 0 and variance sigma squared. Take a sample size of n. We're going to conduct an alpha level test. And the null hypothesis is that the variance is between two values. Oh, that should be a sigma 2. I don't know where my pen is. Versus the alternative that sigma squared, the variance is less than sigma 1 squared, versus that it is greater than sigma 2 squared. Now, the density for a normal distribution looks like this, and then it can be I'm going to call it transformed to look like an exponential form. So this is out front. So this is a function of the unknown parameter. And then this is a function of our data and the unknown parameter, which is sigma squared. And then so our test statistic, according to the theorem, is the sum of the xi squareds. Now it's sufficient for sigma squared, but note that y divided by the variance, the true variance, is a chi-squared random variable with n degrees of freedom. Or you can think of it, if you multiply the sigma squared up, y is distributed a constant times a chi-squared with n degrees of freedom. Now note that minus 1 over sigma squared, which is what this is, it's a one-to-one function of sigma squared. You can back solve for sigma squared to be minus 1 over 2 tau. And since they're one-to-one functions of each other, tests for tau and tests for sigma squared are 100% equivalent. So then according to the theorem, the UMPU, unbiased, uniformly most powerful unbiased test, is given by this test function. So phi, which is a function of our data, it's 1, meaning reject the null hypothesis if our test statistic is less than some C1 or greater than some C2, and do not reject, which is 0, if it's between these two values. Now, one thing we're going to make use of is if we divide everything by a known constant, it doesn't change the probabilities or the overall test for our test. So at points in the video, we're either going to divide by sigma 1 squared or sigma 2 squared. And so I'm going to just call it sigma I for illustration here. So if we divide everything by sigma I squared, then it transforms into this. And the reason we do that, because then this becomes a chi-squared distribution. And it makes calculating things easier. But ultimately we want this. That we want to know C1 and C2. Now C1 and C2 are derived by this equation. So we're going to let Wi in the development below be just y divided by sigma I squared. So W1 would be y divided by sigma 1 squared. And to determine these constants, we have two equations. So it's expected value of the test function, assuming sigma 1 squared is the true value, is equal to alpha. And we get sigma 1 squared because of this. And then we're going to assume sigma 2 is squared for the second equation. So the second equation is expected value of the test function, assuming sigma 2 squared is the correct variance, is equal to alpha. So now let's start solving for sigma or C1 and C2. So the first equation, alpha is equal to the expected value of this test function. Since it's discrete, It's 0 times the probability of it happening, or 1 times the probability of happening. So we're just left with this. And here we're making use of this second test, right? So W1, which is y divided by sigma 1 squared, is less than or equal to sigma 1 prime, right? And then we get plus W1 is greater than C21 prime, assuming sigma 1 is the correct value. Now, here we have to assume that, you know, if we split alpha, say, into alpha 1, 1 and alpha 2, 1, and the second index, the 1, means that we're assuming sigma 1 squared is a true variance. Then, see, this is a chi-squared, so this piece has to be, say, alpha 1, 1, and then this piece has to be alpha 2, 1. So they have to sum to alpha, right? But that means this is equal to C11 prime is that the alpha sub alpha 1, 1 squared, that's the constant that makes that alpha 1, 1, right? That value is this. And then this value is the chi-squared 1 minus alpha 2, 1, right? It's what makes the right tail alpha. And then you can, and since this is C11 prime is actually C1 divided by sigma 1 squared, you can solve for C1 and get this. And you can solve for C2 and get this. So this equation and this equation we're going to use. Now notice that there's 2 unknowns here. Now this is sort of unknown, but if you cycle through different values of alpha, then it's known. Sigma 2 squared, or not sigma 2 squared. Yeah, well, in a sense, we're assuming sigma 2 squared is true. So the second equation is alpha is equal to the expected value of this test function, which is this. Now we let alpha equal alpha 1, 2 and plus alpha 2, 2. And the second 2 means we're assuming that sigma 2 squared is the correct value. So that means that the constants are determined, right? They have to equal that alpha cutoff value that makes this alpha 1, 2. And then this C2 prime has to equal the chi-squared value that makes that right tail alpha 2, 2. So when you add these two probabilities, you get alpha. But you can back solve for C1 and C2, right? Because this C22 prime is, you know, C2 divided by sigma 2 squared, which is what this is. So here, now look, we have one equation, 2 equations, and 2 unknowns. 2 equations, 2 unknowns. We can solve for that. Now, it's not easy to do it by hand, so we're going to use R to solve these. And in the next video, I'm going to show you how to just instantly solve those. Now, before we quit, I always like to have sort of a comparative test or an approximate uniformly most powerful unbiased test. And I call it the leave out one tail test, because these are so easy to calculate. And if I didn't have R to do it, this is the way I'd do it, because it's going to be pretty close. So you let alpha just be the probability that our test statistic is less than C1 prime. And then that forces, then we know C1, it's equal to that alpha, you know, the chi-squared cutoff value that makes the tail alpha. And then you can back solve for C1 and get this. And we're done. That's C1. That's the C1 to use. And then you can do the right tail, that the test statistic is greater than some, you know, C2 prime. And then so C2 prime is the alpha value that makes that right tail alpha. So that really should be 1 minus alpha. Darn it. And then, and that's it. So we've solved for C2. And we're done finding the rejection region. But this is only approximate. But it's so easy to find. I don't know why this has never been taught, because it's so easy. The example we're going to do for the R illustration is this. We're going to assume our data is normally distributed with mean 0, variance sigma squared. We're going to take a sample size of 55, conduct the test at 0.05. The null is that the variance is between 9 and 11. The alternative is that it's less than 9 or greater than 11. The uniformly most powerful test cutoff values are C1 is equal to this, 349. C2 is equal to 813. Now doing the leave out one tail test, C1 is this value and C2 is this value. So they're sort of close, and the further these two values go apart, the closer these are in agreement. But the power curves for these two tests are very similar, very close. All right, well, that's all I have. The next video is going to be an R illustration of this example, and hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.